Let's extend what we found of finding the surface area of space curves to looking at surface integrals. So instead, before we were just trying to find the area of each of these tiny little parallelograms, suppose that this space curve in space is sort of like a level surface of some type of in a space that's taken up by a density function. So every point in here in R3 in my x, y, z space has some output w that tells you what the density is right at that point. And I want to find what's the total mass of the surface. So I need to add up all of the little densities at every single point everywhere along this surface. And the way to think about doing it, or the way that we're going to think about doing it, is we're going to approximate space by these parallelograms again. And in this case, what is the density? Well, we want to find the mass of the entire surface. What is the mass of one of these tiny little parallelograms? Well, it's going to be the density of the parallelogram times the area that that parallelogram is taking up. And if these parallelograms are sufficiently small, the approximation will be sufficiently close to what the mass would be. Well, I guess each parallelogram will have relatively uniform density. And as we take the limit using calculus, it means that we're going to get the exact value of the mass of the surface. So what did I just say? That's essentially just saying that in order to find the surface integral, we are going to take the area of each of these parallelograms, and recall that the area of the parallelogram is given by the magnitude of the normal vector. And then for each parallelogram, I'm going to multiply that by the density at that place, which is given by the function. We're thinking of this as a density function. And our bounds in this case of integration are just going to be the bounds. Let's see, I put u on the inner side and v on the outside, just like before. So really the calculation is pretty straightforward. If I ask you to compute a surface integral, really we're just integrating over this function, but then we're going to multiply it by the area of each of these tiny little parallelograms. Let's see an example to see what this looks like in action, because maybe the one step that's sort of suppressed is the fact that this integral is in terms of u's and v's, and this f is in terms of x, y's, and z's. So we're going to actually have to plug in our parameterization to be able to get rid of our x, y's, and z's and turn them into u and v's, depending upon how we parameterize this surface. So let's look at an example. We're going to use the same cylinder as we did before, only this time we're thinking of our space as having this density function. And so as we sum up over the surface, each part of the surface is going to have a different density, and we want the total mass. So let's use the formula that we had before. Recall that this is just going to be the double integral of our function f of x, y, z times the magnitude of the normal vector. And this notation might make some people hurt. Our u's in this case, I guess we let go from 0 to 2 pi, and our v's we let go from 0 to 3. But there are some pieces that are troubling. So the first troubling piece is the fact that this has to be rewritten in terms of our parameterization, right? So let's rewrite that first. F of our parameterization of uv is going to be equal to x times y. Well, in this case, x is exactly equal to 2 cosine u, and y is equal to 2 sine u, and then plus z. Z in this case is just equal to v. And so this is a way that we can rewrite our f function in terms of the variables that we want. And I'm going to rewrite this as 4 cosine u sine u plus v. The second step is to compute our normal vector. Normally, in order to compute the magnitude of our normal vector, we would first have to find each of our unit tangent vectors, take their cross products, and then find the magnitude of that. Thankfully, this is the same function that we did before, and we found last time that I think in this case our normal vector had a magnitude of 2. One note is that this might not be a constant. In this example, the magnitude of our normal vector was 2. Sometimes it's going to be a function of u's and v's. You could see how that might happen. And if it is a function of u's and v's, that's not a problem because we can integrate with respect to u and v. But just to keep that in mind, that this is not always a constant. So really, we've set up our integration, and now comes the boring part of integrating. You're welcome to stop the video here if you don't want to watch me go through some tedious steps of integration, but if you'd like to practice, you're welcome to follow along. It's going to be the integral as v goes from 0 to 3, as u goes from 0 to 2 pi, of our function that's been simplified for cosine u, sine u, plus v, and all of that is multiplied by the magnitude of our normal vector, which is 2, du, dv. So I'm going to multiply this through, and I see that I get 8 cosine u, sine u, plus 2v, du, dv. My first integral is with respect to u. This actually is a little messy. It's not as straightforward as I thought. I'm going to break this up into 2 separate integrals, and we're going to treat each of them separately. The first integral, I'm pulling out the constant 8 cosine u, sine u, du, plus the other integral is just going to be 2 times v, so it's 2 double integral of v du dv. Let's just focus on this first integral because this one actually requires a u substitution. Notice that if I let sine of u be equal to, I guess I shouldn't use a u substitution, whoops, du dv. I'm going to use a w substitution for the second one. Let's go on a separate page to do out our scratch work. Here we go. So I'm going to let w equal to the sine of u, because then dw is going to be equal to the cosine of u. And when I do this integration, that means that du, I can rewrite this first integral. This is 8 times the double integral of the cosine term gets combined with the du term to become my dw, and I'm left with just w dw dv. So I can integrate w with respect to w, and that becomes 1/2 w squared. Whoops, there's only one integral left because I just integrated. And we're evaluating this as u goes from 0 to 2 pi, but of course we don't want to evaluate as u goes from 0 to 2 pi, because this isn't a u, this is a w, and our bounds have to match the variable. So I end up with 4 times the integral. I'm going to convert back to saying that my w is actually equal to the sine of u. And now I'm going to evaluate because now u matches the original bounds. I'm plugging in 2 pi. The sine of 2 pi is 1. So this is equal to 4 times the integral. Oops. This 1/2 is where the 4 went to. Okay. Sorry. So I did 8 times 1/2 to get the 4, so there's no 1/2 left here. But what is the sine of 2 pi? The sine of 2 pi is 1, but the sine of 0 is 0, but it's also 1. And so this whole thing is going to be 1 minus 1, which is 0. So this is 4 times the integral of 0 dv. Uh-oh. So it means that this whole first integral, all of the work that we did, what's the integral of 0? So now we're just left with 0 for this first integral. right? Because the integral of 0 is 0, and we're left with 0, so that's all very unsatisfying. But notice that that's only one part of this summation. So let's do the second integral piece, the second term. It's the integral as v goes from 0 to 3, and as u goes from 0 to 2 pi of v du dv. So integrating with respect to u, I get du, and I'm evaluating u as it goes from 0 to 2 pi, and that's going to end up being 2 pi times v. So I'll pull that out front and get 4 pi v equals 0 to 3 of the integral of v dv. Integrating v, I get 1/2 v squared times 4 pi, evaluated from v equals 0 to 3. Plugging in 3 squared is 9, and 4 divided by 2 is 2. So this becomes 18 pi. And that's our final answer for the integral over this particular cylindrical surface for this parameterization, and actually it's independent of parameterization. I could have done a different one. So if I'm thinking of this as a density function, I've just found the total mass, which is a different value than the surface area that we found previously.